In this video, I am going to explain the concept of action potential. And action potential is basically the mechanism used by a neuron to transmit signals along the axon. So very quickly, just to refresh your memory, here is a typical neuron, and you will have the axon right here, and action potential is the mechanism used by a neuron to pass signals down its axon. Okay, so for simplicity, I'm going to go through just basic transmission with no myelin, and once you've understand that, then we can extend the concept to myelinated axons. So before we talk about action potential, there are a couple of things I need to review with you, and the first one is what we call the sodium-potassium pump. Okay, so sodium-potassium pump is a membrane protein, and you will find this membrane protein along the entire length of the axon. So let me just draw a zoomed in version of the axon for you. So here we go. This is the cytoplasm, and on the outside, this would be cytoplasm, and on the outside we would have the extracellular fluid. Okay, the outside, the inside, and on the membrane we are going to have these sodium-potassium pumps. Okay, shown in purple. So the sodium-potassium pump, its function is to transport sodium out of the cell, right? Out of the cell, and it's going to transport three sodium. And for every 3 sodium it pumps out of the cell using ATP, of course, it's going to transport 2 potassium into the cell, right? So 2K plus. And if you let this happen continuously, ultimately what you will end up having is high sodium levels on the outside and low sodium levels on the inside. Similarly, you would have low potassium on the outside and high potassium on the inside. Okay, and so this is active transport, not surprisingly, because if you keep on pumping sodium out, you are actually pumping it against its concentration gradient from an area of low concentration to an area of high concentration. And same thing for the potassium. A second thing that is worth talking about is every cycle that the sodium-potassium pump works, you are essentially losing a positive to the surrounding, because you are only bringing in 2 positive charges while you are losing 3 positive charges each time. So for that reason, over time, the outside of the cell membrane is going to be relatively positive compared to the inside. Okay, so this neuron here, the axon of this neuron, is going to be what we call a resting neuron, because it is not yet transmitting a signal. And when a neuron is at rest and we measure the charges difference across the membrane, right, we would have a membrane potential of approximately -70 millivolts. All right, so voltage is a measurement of charge difference between 2 points, and because the charge difference is very small across the membrane, it's measured in millivolts, right? There are 1000 millivolts in a volt. So you are probably familiar with the concept of voltage. If you think about a battery, right, you would have like a 9-volt battery, which means the charge difference from the positive and negative terminals is 9 volts. So right now, just remember this number, this -70 millivolts, is created by the sodium-potassium pump, and it means the inside of the cell membrane is more negative compared to the outside. Okay, now at this point the neuron is at rest, meaning it is not transmitting a signal, and so this membrane potential at rest is sometimes called the resting potential. Okay, resting potential. So if you are following along, and if you have paper, what I encourage you to do right now is to take out a blank piece, and we are going to draw a graph together. Okay, and the graph is going to map out the change in membrane potential. Right, we're going to put millivolts on the y-axis over time, and this is milliseconds. Okay, when the neuron is at rest and is not doing anything, we are going to start with this minus 70 millivolts, and it's going to stay there. Right, we call this resting potential. All right, so it's going to stay there for some time. At this point, we are going to have low sodium on the inside of the cell, and we will have high potassium on the inside of the cell. And this resting potential is created and maintained by the sodium potassium pump. Okay, so the sodium potassium pump is what allows the resting potential to form in the first place. So go ahead, pause the video, and try to recreate this, and we can add more to it later on. Okay, let's go back to this concept here. Before we talk about what an action potential is, there's another thing that I need to explain to you first. So number 2. Sodium potassium pump is not the only protein pump that you will find in the membranes of an axon. You will actually find these things called voltage sensitive or voltage gated ion channels. So there are 2 types of voltage gated ion channels. We have one for sodium, okay, and we have one for potassium. Okay, they are voltage gated in the sense that whether the channel opens or not is going to depend on what the voltage is on the membrane of the axon, and so each of these channels are going to open at a particular voltage range. So for example, right, let's just draw what they look like. Right, so I can have the membrane here, and we would have a sodium channels here. You can think of them as like doors, right? And you know, this is one side of the door, and this is the other one. And then currently, this is a closed sodium channels. All right, and then when the voltage reach a particular number, then the channel is going to open, and once the channel opens, it will allow sodium to move across the membrane. Right? Normally, when they are pumped out by the sodium potassium pump, they cannot come back in because charged particles don't cross the cell membrane easily. By having an open sodium channels, that's the only way for them to move across the membrane. All right. So roughly speaking, the sodium channels they will open between the range of minus 60 millivolts, and then they will close at around positive 30 millivolts. Okay, and once you go beyond the 30, or once you've reached 30 rather, then the sodium channels are going to close. Similarly, we would have these potassium channels, right? So they are normally closed, and then when your membrane is at a particular voltage, then they will open, and once they open, the same thing happens. Opening the potassium channels will allow the potassium to move across the membrane. So they too have a special number. Their opening range, right? You can think of these as kind of like, you know, business hour of your favorite store, right? They will only open between that and that. And for potassium channels, the doors, the gated channels will only open between positive 30 to negative 90, we will say, okay, millivolts. Okay, so these numbers are just roughly speaking, right, depending on which textbook and how advanced the textbook you're reading, these numbers might change slightly. But for my course, right, that's what I want you to know. Right? Another thing is this. There is an important concept called refractory period. Refractory period. Okay, and refractory period is basically referring to a short time where the channels will be non-responsive during that time. So once the sodium channels are closed at 30 millivolts, it will then enter the refractory period, which means during this time, no matter what you do to it, it's not going to open. Even if you reach minus 60 again, the sodium channels will not open at that time because it's sort of resetting itself, right? So refractory period refers to a short period after the channel closes where it is resetting itself so that it will be able to respond again. And this is quite important, as you will see later on in the video. So those are the key things to remember for action potential, right? We will now talk about what happens when a signal actually arrives. So this is your typical neuron again, and what we're talking about next is when the neuron receives a stimulus from something else, right? And it decided to pass it on along the axon, right? How exactly does it do it? When this happens, the membrane proteins are going to respond a little bit differently. So here, let me draw out the axons for you again. Okay, so again, we have the cytoplasm, and then we have the ECF here. So when a signal arrives, what's going to happen is it will push the membrane potential towards positive. All right, so why exactly does that happen? We will explain shortly, but for now you just kind of have to believe me. If there is a stimulus that arrives, then it will push the membrane potential slowly towards positive. So if we go back to our graph over here, when a stimulus arrives, right, I will use a little lightning bolt to show that. When a stimulus arrives, your membrane potential will slowly increase. It will slowly become positive until it crosses a line. Okay, and we call this the threshold potential, right? So this right here, threshold. And once you cross the threshold potential, you might remember minus 60 is actually the magic number for the sodium channels to open, right? So let's go back and see what happens. At the beginning, because of the sodium potassium pump, we have high sodium on the outside and low sodium on the inside. And these sodiums would naturally want to come back in down their concentration gradient. But they couldn't do it when the neuron is at rest because all these sodium channels are currently closed. But when a stimulus arrives, it will cause the membrane potential to move towards the threshold. And once you cross the threshold, what will happen is you've reached the opening voltage for the sodium channels, and that will cause the sodium channels to open. So here is an open sodium channels. For simplicity, I'm not going to draw the sodium potassium pump anymore. And when these sodium channels open, all the sodium from the outside is now going to move inside. So let me show that using red dots. So you will have all these sodiums coming in, okay? Right. You will still have some on the outside, right? Now, farther down the axon, the sodium channels are still closed because the signal haven't gotten that far yet. And so for the later part of the axon, you still have low sodium on the inside and relatively high sodium on the outside. Okay, so let me just put that down for you. We will have low sodium now because they just moved in, and we would have high sodium. But farther along the axon, it's still at rest, so nothing changed compared to the original. You still have low on the inside and high on the outside. Okay, and potassium at this point is still the same because the potassium channels are still close. We have not reached that number where the potassium channels are going to open yet, and so the outside will have low potassium, and then you would have high potassium inside, right? Same thing over here, high potassium on the inside and low potassium. Okay, so I'm not going to write that down, but that's what it is. So on a graph, what does it look like? Well, after the sodium channel opens at the threshold, and you saw on the drawing, there will be a lot of sodium coming into the cell, and all that stuff coming in will cause the membrane potential to become positive, right? All these influx of sodium will push the membrane potential towards positive, up, right? So this phase is what we call depolarization. Okay, and it's primarily caused by the influx, right, the moving in of sodium into the cell. But it's not going to increase forever, because if you remember, when you reach 30, right, when you reach 30, that is actually the closing point for the sodium channels. Sodium channels only open between -60 and +30. So when enough sodium comes into the cell, pushes it towards 30, at this point, one of the things that happens would be sodium channels close, right? And they enter the refractory period that we talked about. So let's go back here and see what happens. Once these sodium comes in, we will now close the channels. Right, we will close the channels, and no more sodiums are going to be able to move. So at this point right now, we are positive inside, right? Positive 30, if you remember, and it will be negative outside. But farther down, it will still be negative, because the signal haven't got there yet, and then it will be positive on the outside, right? In fact, here it's approximately -70 millivolts, and over here is positive 30 volts, right? So a couple of important things happen here, right? The first one is, the sodium channels closed, like I told you, and the second thing is, if you think about the concentration of sodium right here, the concentration of sodium is high because of all the stuff that came in. Farther down is low because it's still at rest. So it's not surprising that some of these sodium would like to move forward, right? Some of these sodium would like to move forward, and as that happens, right, it's going to bring some positive charge farther down the axon, and that will cause the -70 to slowly become -60, pushing the next section over the threshold, and the same thing would happen in the next section as it just did for this current section. So remember at the beginning I said, a stimulus arrives and it pushes the charge towards positive, and that's what I meant, right? Some sodium from the previous section is going to move forward and then pushing it over the threshold, and then you will have the depolarization happening in the next section. So the second point that I want to write down here is number 2. Although the sodium channels of the current section will close, sodium channels farther down the axon opens, and it causes it to undergo depolarization. And the last thing that will happen, and I'll put it right here, the last thing that would happen is we are now sitting at 30, and that actually is the opening voltage for the potassium channels, right? For the potassium channels. So going back here in our drawing, right? These potassium channels, they will now open. They will now open. And when they open, all that potassium that were inside will now have a way to exit, right? And think about it. These potassium actually really want to leave the inside of the cell for 2 reasons. Number 1, it was high concentration on the inside and low concentration on the outside, so naturally they would want to go down their concentration gradient. But the second reason is because of the sodium influx that happened earlier, the inside is extremely positive right now. And as you know, positive charges, they like to repel each other, right? So all these sodium, they can't go anywhere because the gated channels for them are closed, and the potassium are the only ones that can go far away from other positive charges. And so you will have a lot of potassium leaving the cells, okay? So much so that it will cause the membrane potential to drop once again. So it's going to go down, 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 down. And because there is so much potassium leaving, you will go beyond your resting potential of minus 70, right? In fact, you're going to go all the way down to approximately minus 90 millivolts. Okay, so this dropping of your membrane potential, right, becoming negative again, is what we call repolarization. And this repolarization is caused by the efflux, right, leaving, right, of potassium ions. So between positive 30 and negative 90, that's when the potassium channels are going to open. So just an important point here, you can see on the way down, the graph actually reaches the threshold again of minus 60. So one might think, wouldn't the sodium channels open again because minus 60 was the magic number for them to open in the first place? Well, the answer is no, because if you remember, the sodium channels are still in refractory period, and that's why the refractory period is so important, because if there isn't a refractory period, then you're right, the sodium channels would open again, and the whole thing would just fluctuate up and down and up and down, and the signal would be all over the place. So that doesn't happen. So now the signal is going to come back down. Just backtrack a little bit, right? At this peak point here, if you think about the concentration of the ions, it's actually going to be high sodium because of the influx, and you are going to have high potassium, which is the same as beginning, because up to this point, the potassium channels hasn't opened yet, and so it's going to be the same concentration as before. At the bottom here, the sodium is going to be high because of the influx, and they haven't had a chance to leave yet, and the potassium is going to be low because they've just exit through the efflux, right? So it's quite interesting at this point right now. There are 2 problems. Number 1, we are way too negative. Okay, we are way too negative in the potential, right? We should be back at minus 70 in order for me to go back to resting potential. And if you look at the ion distribution, right? The ion distribution is actually completely opposite to what you want in the resting potential. So we got to fix these things. We got to fix the negative 90. We got to bring it back to negative 70, and we need to redistribute these ions concentration. So in order to do that, we are going to need to have our sodium potassium pump. right? So at this point, the potassium channels are closed, the sodium channels are still refractory, and the only thing that's working, so to speak, is the sodium-potassium pump, which would take these extra sodium, send them back out to the ECF, the extracellular fluid, and we would bring back potassium in. And slowly, they would go back to -70. And when another one goes back to -70, it is ready for another round of signal transmission. So action potential is actually referring to this part right here. Okay, this is the temporary reversal of membrane potential, right? It used to be negative on the inside, but it will temporarily flip to positive on the inside, which in turn causes the next section to flip to positive, and so on and so forth. And ultimately, you are going to be able to transmit a signal down the entire axon. So I just missed a single a word here. This point where it is more negative than your resting potential, this is called hyperpolarization. Okay, and again, to restore it, right, from polar hyperization back to normal, we would need the sodium potassium pump. Okay, so that's action potential. Just go through the whole concept again on your own. Read notes I post online, and it should make sense. Thanks for watching.